This is some brief direction and teaching and a tutorial dealing with colligative properties. Colligative properties are usually divided into four categories. So, vapor pressure lowering, which was discussed in an earlier video, boiling point elevation, freezing point depression, and the impact upon osmotic pressure. If we understand the theory behind what the presence of a solute does to the behavior of a solvent in affecting its vapor pressure, that then has consequences on the boiling point and the freezing point. We then need to look at the role of the solute upon the behavior of the solvent and how that just affects the probability of the solvent being able to find holes in a permeable membrane. That's osmotic pressure. So, as stated, with boiling point, the presence of a solute elevates or raises the boiling point. And the freezing point, we call it freezing point depression, it is lowered. The change in our boiling point or our freezing point is directly proportional to the molality of the solute in our solution. Now, the reason why we're using molality is because we're changing the temperature of our substance. We know that molality is mole of solute per kilogram of solvent. And with temperature, grams and moles are unaffected. But if we use molarity, volume would change with changes in temperature. So that is why molality is favored here. The K sub B and K sub F are the boiling point constant and the molal freezing point constant. And it is dependent upon your solvent. You would be provided those values. So this is actually from modern chemistry. We're usually dealing with water. We're going to be cited the normal freezing point, and you're only expected to know the normal freezing point for water and the normal boiling point for water. You would be provided, we're not expected to memorize these either, the negative values of K sub F's and K sub B's for different solvents. It's particular to the solvent. What you are solving for is the change in your boiling temperature or freezing temperature. Usually, it's given as a delta lowercase t sub f, because we want to make sure that we just designate between the change in the freezing point and the actual freezing point, the change in the boiling point and the actual boiling point. Remember, the boiling point is when the equilibrium vapor pressure equals atmospheric pressure. So, if the presence of a solute lowers the vapor pressure of the solvent, we know that we can increase vapor pressure with increases of temperature. So, if the presence of a solute naturally lowers the vapor pressure, that means we're going to have to add more energy so that vapor pressure will equal atmospheric pressure to boil. So a solution has a higher boiling point than its pure solvent for that reason. Well, a solution freezes, or a solvent, a liquid freezes when the vapor pressure of the liquid equals the vapor pressure of the solid. It's very, very strange to think about a vapor pressure of a solid, but we know we're always going to have some sublimation and some kind of equilibrium in a closed system. Well, if the presence of a solute lowers the vapor pressure of the liquid, it's when these two things are equal that we will have freezing. So, to get the vapor pressure of the solid to equal the new lowered vapor pressure of the liquid, we need to actually decrease the temperature. So that is why the freezing point of a solution occurs at a lower temperature. Here is an example problem. We are being asked here to determine the mass of the solute that will cause a change in the freezing point of the then solution. Now, what we have to realize is the change in our freezing temperature here is negative 23.3 because the freezing point of water is 0. So, what I did is solved for the molality of my solution, so inputting my change in my freezing point divided by the molal freezing point constant, which is dependent upon the identity of the solvent, and this is the value for water. We get this molality. Well, I know molality is mole per kilogram, and I'm being told that I'm using 10 liters of water. So using the density, I got the mass in kilograms. So I found the molality with this. Then expanding the molality and multiplying by the mass of my solvent, I'll then have the amount of moles of the ethylene glycol that we need. Then converting to grams, we get that. We often are asked for molar mass. So, if a certain quantity of solute was added to a certain quantity of solvent, and it had a boiling point of this. Now, we know that water boils at 100, so if the solution is boiling at 100.34, my change in my boiling point is 0.34. It's asking, since you dissolve this amount of glucose and this amount of water and had this impact on the boiling point, it's asking us to find the molar mass of the glucose. Molar mass, gram per mole, gram per mole, gram per mole. We're given the mass of the solute we added to have this impact. So we need to find out how many moles this represents. So I already have my numerator, I just need to find moles. So if we know the change in the boiling point, water gives us the K sub B value. If I can find the molality, it will get me moles. I'll then plug in. So that's exactly what I did. I took the change in my boiling point, divided by the K sub B for water, then multiplied my answer by the kilograms of water that I added, then taking the 18 grams divided by the 0.1 moles, we get the molar mass. Now, here is just another example of finding molar mass, but it's dealing with freezing point. And if we just remember that molar mass is gram per mole, well, you're ultimately going to divide this 0.546 grams per the amount of moles that you would find with the freezing point depression. So, we are dealing here with benzene. So, what I'm being told the freezing point depression. So, in other words, I'm being told that my change in my freezing point is 0.240 degrees Celsius. So what I need to do is find the K sub F for benzene. So we would look to a table. Don't you know? Having trouble finding that. We would input the K sub F then for benzene, find the molality, multiply that, since this will be then mole per kilogram, by 0.0150 kilograms of benzene to get the moles and then plug it in there. I unfortunately am without the K sub F of my benzene, but if you looked at my scan notes, then you'll find my work. But this is so similar to the previous example. Here is just a reminder of what the presence of a solute does. So if this is the phase diagram for the pure solvent, the presence of a solute lowers the freezing point. and increases our boiling point. Do you see? So it actually expands the regions in which we encounter the liquid state. So this is just a nice confirmation with the phase diagram of what the presence of a solute does. All right, this is our equation for osmotic pressure. Because we are not looking at the impact of the change of our temperature, we will use molarity. Osmotic pressure is usually this kind of pie-looking symbol, and we will find that by taking molarity times R times our temperature. Okay, osmotic pressure. If we have a pure water sample, if I would place another vial inside of there, and the vial was separated from the pure water by a semi-permeable membrane, which means there's holes in the membrane that will allow for some molecule passing back and forth. Well, if it's pure water on the outside, but I have a solution of sodium chloride, which we know because of dissociation will be separate sodium ions and chloride ions. What we'll actually find is flow of the solvent into the solution. And this would be why. We have our water molecules, which we know are Mickey Mouses. Yeah. And if this would be where our sodium ions are and our chloride ions, and we know that the sodium ions will be smaller than the chloride, but not worried about size at this point. Well, the water is going to pass through when it encounters one of the holes. Well, just what is the probability? Water, because you only have water on this side, it's just more likely to find a hole in the membrane. Well, here, water can find the hole, but so also can the ions. Now, we manufacture the membrane to be large or small, depending upon if we want solute or solvent to pass through. So we may have engineered this so that only the water molecules can pass through, or maybe the water and just maybe the sodium ion, and so on. But if we're looking at this, why do we have the massive movement of pure solvent into the solution? It's not because the solvent knows that this is a solution or more concentrated. It's just sheer probability. Well, we can stop the flow of the water by exerting a pressure upon this solution that will not allow for any volume change. Well, that would be the osmotic pressure. You can take a look at my notes to see the problems that I've solved here, but that gives an idea of the theory of osmotic pressure. Best of luck with the problems, and as always, you can email any questions my way.